Okay, so let's talk about infinity. In physics, infinity's kind of a dirty word. For decades, it's been the place where our best theories just break. It's the error message that tells you you've done the math wrong. But what if it's not an error at all? We're going to explore a wild new theory today that completely flips the script and asks, what if infinity isn't the problem? What if it's the answer, the raw material the entire universe is built from? The question is, does this idea have what it takes to become the undisputed story of what a particle is? So here's the game plan. First, we're going to dig into why infinity has been such a massive headache for physicists. Then, we'll look at the new cosmic blueprint this theory is proposing. After that, we'll see how a stunningly beautiful order can actually emerge from all that chaos. We'll use this idea to solve a huge puzzle in particle physics, and finally, the most important part, we'll see how we could actually test if any of this is for real. Right. So imagine you're a physicist. You're working on some beautiful, elegant equation to describe the universe, and then, bam, your calculation spits out the number infinity. Well, that's not a good thing. It's a giant red flag. It's basically the universe telling you, nope, you're wrong. Your theory has hit a brick wall. Whether you're talking about the singularity at the heart of a black hole or the energy of a tiny quantum field, infinity has always meant one thing: breakdown.
But this is where things get really interesting. This theory asks a crazy question. What if we've been reading that error message all wrong? What if infinity isn't the brick wall at the end of the road? What if it's the road itself, the starting point, the raw, untamed potential from which everything we know, every single particle, force, and law of nature is carved?
So, how in the world do you build the universe out of pure infinity? Well, the theory lays out a new framework for it, a kind of cosmic recipe called the sci-fi theta paradigm. You can think of it as a simple three-step process for creating reality from the ground up, starting with nothing but pure, unstructured, infinite potential.
Okay, so let's break that down. Step one is psi. This is your raw material, an infinite, formless block of clay, just pure potential. Step two is phi. Now that clay needs to be shaped, right? Phi represents a fundamental rule of symmetry, like the potter's hands that come in and start carving order out of the chaos. But wait, where do you start? In an infinite block of clay, every point is the same. You need a fixed reference point, an anchor, and that is step three, theta, the unmovable spot where it all begins.
And this anchor, this theta, is an incredible concept called not infinity. It's a point that is so self-referential, so fundamentally stable, that even when you apply the universe-shaping force of symmetry to everything, this one little point stays put. It doesn't move. It becomes the "you are here" marker on the map of reality, the origin point from which all other structure can emerge.
So, we have our ingredients: infinite potential, a rule of symmetry to shape it, and a fixed anchor point to start from. What happens when you put them all together? You might expect an even bigger, more complicated mess, right? But that's not what happens. Instead, out of pure chaotic infinity, something incredible emerges: order. And the results of this cosmic recipe is something the theory calls the golden set. This is the core idea. When you take infinity and you apply symmetry to it, you don't just get more infinity. You actually get a finite, stable, and beautifully structured reality. You get a finished sculpture. You get a universe. No, it's not called the golden set just because it sounds cool. It's called that for a very specific reason. Because when you look at the deep mathematical structure of this reality, a very famous number just pops right out: the golden ratio, phi. Yeah, that phi. The same irrational number you see in the spiral of a galaxy, the shell of a nautilus, and even ancient works of art. So why is phi so important? Well, it turns out the golden ratio is the perfect mathematical sweet spot. It's the ideal balance between something being rigidly ordered and predictable and something being completely chaotic and random. It's the signature of a system that can be infinitely complex and detailed without ever just repeating itself. It's like nature's secret recipe for building things that last. All right, this is all fascinating stuff. I mean, building a universe from math is pretty cool, but does it have anything to do with our universe? To find that out, we have to put it to the test. And this theory goes right after one of the biggest, most nagging puzzles in all of particle physics: the generation problem. So here's the mystery. We all know the electron, but it has two siblings: the muon, which is about 207 times heavier,
and the tau, a real heavyweight that's almost 3,500 times heavier. The weird part is, other than their mass, they're identical. Perfect clones, same charge, same spin, same everything. Our current theory, the Standard Model, just accepts this. It has no explanation for why there are three of them. This new theory, though, walks in with a breathtakingly simple answer. It says, they are not three different particles. They are one single fundamental particle that is simply existing in three different energy states. You can think of it just like water. You can have ice, liquid water, and steam. It's all just H2O, but with different levels of energy. And the way it proposes this works is by imagining the particle not as a tiny dot, but as a topological knot of energy. And each of the three generations we see is just an extra twist in that same knot. The more twists you add, the more energy gets stored in the knot's shape, and from the outside, we perceive that extra energy as extra mass.
So, in this picture, the electron is the ground state. It's the simplest, most stable version of this energy knot you can have. It has the lowest possible energy, and that means it has the lowest mass. It's the base knot.
Now, what happens if you add another twist to that knot? Well, it takes more energy to hold that more complex shape. And boom, you get a muon. It's the exact same underlying thing, it's just in its first excited state, making it more massive. And if you add a third twist, you get the super energetic and very heavy tau particle. But here's the truly brilliant part. The theory also suggests that if you try to add a fourth twist, the knot just becomes unstable. It would immediately unravel. And that gives us a natural built-in reason for why we only ever see three generations of these particles, and no more. Now look, that is a beautiful story, right? It's neat, it's tidy, it makes sense. But in science, a good story is never enough. For a theory to be a real contender for the truth, it has to stick its neck out. It has to make concrete predictions that other scientists can go out and test and potentially prove wrong. It has to be falsifiable. And this is where the theory really shines. And these aren't some vague, hand-weavy predictions. They are incredibly specific. It predicts we should find subtle patterns based on the golden ratio hiding in places we thought were totally random, like the distribution of prime numbers. It predicts the exact mass ratios for some really exotic particles called glue balls. It lays out a precise mathematical relationship for the magnetic properties of the electron, muon, and tau. And of course, the big one, it states unequivocally that we will never, ever find a stable fourth-generation particle. Each one of those is a clear target, a line in the sand. So in the end, we're left with this final, absolutely mind-bending thought that this finite universe, with all its structure and its intricate laws, might not be something separate from infinity at all. It might be infinity, just viewed through a very special kind of lens, a lens forged from symmetry and anchored by a knot. Is this the real story of particles? The idea is elegant, the solutions are compelling, but in science, nature always gets the final say. The only question now is, what are we going to find when we look?